This computer. Awesome. Welcome, friends. Another fun adventure with Deep Learning Adventures. Thanks for joining us. Thanks to my co-organizers, Robert and David, as well as friends from all around the country and around the world. We are Deep Learning Adventures, and we're a fun, engaging group where we talk about data science, not just deep learning, machine learning, and specifically deep learning in general. We've been going through an adventure with Coursera on deep learning AI. And today you're going to hear a little bit more about that adventure related to TensorFlow datasets. So let me share my screen a little bit so you have a bit more context. So again, if you're joining us from social media or YouTube, welcome again. Thanks for joining us. You can find us on Meetup under Deep Learning Adventures. We try to structure our course in terms of our session in terms of content. So if you notice, the last couple of sessions we had to break them apart because the current adventure that we are doing for TensorFlow Data and Deployment Specialization from Coursera was a little bit too involved. So we broke down week 3 and week 4 into 2 separate sessions. All our sessions are recorded and available on YouTube. For this series specifically, we have a new playlist, DLA, TF, Data, and Deployment. You see that we have course 1 and course 2 recorded here, and we just started with course 3. This specialization is covering different aspects. We started with deploying models on our browser with tf.js, the JavaScript version of TensorFlow. Then we moved to the TF Lite and deploying models on edge devices, like smaller devices like Android, iOS, or Raspberry Pi devices. Then we switched gears a little bit and we're exploring really the TensorFlow ecosystem in terms of reading existing data sets already in TensorFlow, as well as now, as you're going to see today, parsing and really doing that almost that scikit-learn approach that you usually see with different column and field types and all kind of interesting pipelines. This week mentions a few interesting notebooks that David and Robert will mention for us. They're pretty extensive. Again, we're not going to go through all the details, but just to give you an idea of how versatile and how important the TensorFlow methods and ecosystem is. We're just going to look at some examples today. I think that's all I have in terms of resources. Yeah. There's a machine learning course that Google has developed that this course mentions some resources about hash tables. It briefly mentions this NLP specialization that hopefully we can cover sometime in the future, and as well as the notebooks that Robert and David will share with us. Cool. Having said that, let me stop sharing and welcome again, everyone, and turn it over to David.
Okay. Hopefully you can see my desktop now.
And one last thing, sorry, I apologize, David. Yeah, one of the things you're going to see today are coming from Coursera and Deep Learning, so I want to make sure that we pay attribution to them. Yeah, I just wanted to say that.
You want to show it?
Yeah, just for completeness purpose. Yeah. So again, a lot of the materials you're going to see, the slides and the notebooks are developed by Coursera and Deep Learning AI. And we thank them for their hard work and want to make sure that credit is attributed to them. This is not something we put together. Cool. Thanks again. And yep, hand it over back to you, David.
I think Robert wanted to say something first.
Yeah, Yeah, I'll kick it off, and then we'll get to David very shortly. So this course here, as you know, is data pipelines in TensorFlow, and it's course 3 of the data and deployment specialization, as George had mentioned earlier. And as we got into week 3 here, we realized that week 3 was substantially longer than the other weeks. I can't speak for everyone, but I can say that I've probably spent about 4 times as much time going through the content of this week as a typical week. So it became clear to us that maybe we didn't want to cover 2 weeks in one session. That being said, there's a lot of content that we won't, there's a lot of content in week 3 that we will barely touch on as well. Those of you who have attended our meetups, Deep Learning Adventures, multiple times in the past will be familiar with our extremely formal setup here, where we do not allow any discussion or questions or anything like that. That's a joke. This is all,
Sarcasm filter.
yeah. This is there are 12 of us here on the call, and I think that especially in a topic like this, where there are a lot of different directions that we could take this discussion because there is so much content from this week, I highly encourage anybody who wants to ask about any specific aspect of this content, please speak up. Anybody who wants to comment or question, please feel free to take part in the discussion. I really want this to be a discussion amongst all of us, anybody who's comfortable doing so, and I want this to feel like a welcoming group to everyone, old timers and newcomers alike. So with that said, there are a number of things to cover in week 3. I'm going to share my screen and show just the outline of the course. Can you see my desktop?
Yes.
Yeah, so the learning objectives here in week 3, just so we're all on the same page, we want to use different libraries and techniques to export data into new training pipelines. We want to practice with pre-built pipelines, which can improve your development time substantially. We're going to talk about different ways of processing feature columns. We're going to talk about bucketized columns, hashing columns, tokenizing. We're going to look at different data types in the TensorFlow data class. We're going to explore the dataset objects and the different types of dataset objects in TensorFlow. And we're also going to just apply, not only show you how to get the data from sources, but also various operations and transformations in the assignment process as well. And what I think I'll do to kick it off is there's one really long notebook in the course, and this was the one that I spent more time on than any other part of this week. Data.ipynb. It's rather surreptitiously hidden about 2/3 of the way down through the week. So when going through the course, you have no idea what exactly you're in for. But what I'll do is just do the intro for this a little bit to set the stage, and then we'll talk about. Then I'll turn it over to David, and he'll be leading us through a very important unit from the course on feature columns. So are there any questions on the general coverage for tonight and the way we want to interact here? As always, feel free to stop me with questions when we encounter anything that you're not understanding. It's a very small group and a very welcoming group. So this notebook, one of the advantages of TensorFlow is that you are able to create what are known as input pipelines, which is a standardized way of ingesting your data from a variety of sources into a well-defined object called a TensorFlow dataset. And the TensorFlow dataset is a important aspect of the TensorFlow ecosystem. So the TensorFlow Data API introduces this dataset abstraction, and the idea is that you can, no matter what your source of data, if it's something common that other people have tried to turn into a model to be used in TensorFlow, it is probable that there exists some architecture already for getting your data into a format that TensorFlow can handle without you having to write a ton of wrangling code. So this object here, there's a documentation page in the API that describes the object, tensorflow.data.dataset. And you can also view the source on GitHub. And it's, well, it's like looking at Python code, really. There's just a whole lot of methods, and it's probably easier to get the information from the documentation here. You can see there's a lot of methods here. We'll be covering many of those this evening. To get data into a data set, there are really two distinct ways to create a data set. And this is maybe a bit misleading because the second one here is a transformation, which is really already you have to have a data set before you can do a transformation. But sometimes you're constructing a new data set from multiple existing data set objects. The most common way to get started is through a dataset constructor from some other source, either data stored in memory or one or more files. We have basic mechanics. So I think I've run this whole notebook in the background here, so hopefully the results are all showing. So probably the simplest way to start to think about a data set object is to pass it a simple Python list and call the from tensor slices method. That's this one here. There's also a from tensors method, which is much less commonly used, and we'll see why. From tensor slices will take any iterable and slice off the first dimension and assume that that is going to be your samples. And then you will return and you'll just iterate through objects. So we have from tensor slices on a Python list. Each element of that list is a scalar, so we're going to get scalar types back. Here I'm printing these three dataset objects. When we print the objects, we see it shows a tensor slice data set, and the shape of each element is a scalar, which is what that open empty parenthesis means. We can also pass it a multi-dimensional array, and here we have a NumPy array that's 5 rows by 2 columns. And if we look at that one, it slices off and makes each row an element, but now each element has a shape of 2. What happens if we use the from tensors method that I discussed just briefly ago? In that case, you always get a data set that only contains one element. So it's capable of creating a data set, but for most of the uses, the reason that we really want these objects is to be able to iterate through samples in your data stream. So the from tensors just returns a single object of shape 5 by 2. And for that reason, it's just not used very much, but it's a nice example for getting started with TensorFlow. Just to illustrate a little bit further, so we're going to print out the elements in our 3 data sets here. Print out 6 scalars in the first one, print out some 2 tuples in the second one. And when we print the elements in dataset 3, it's just this single element with everything in it. You can also create a Python iterator and define that to go through your dataset, and then you can get them one at a time. Next of the object and convert it to NumPy, and it's just going to show the first one. Now it may be iterable, but you can't just iterate through it directly without wrapping it with an iter object. If you try to do that, you will get an exception here. So if you try to do it without an iterator wrapper, you get an error. With an iterator wrapper, you will get the first element of the dataset. One use case that may be familiar to those who have used tools such as MapReduce framework or some of the earlier big data tools is a reduce transformation, which is a tool that often allows you to take a stored value and process it with some new value that you're reading. So you can start with one value in the queue, and you just reduce it with each of these ones coming in. So what this will do, our reduce function is just adding them. So we get 6, the sum of 6 numbers here is 27. And just to illustrate this concept for anyone who hasn't seen the reduce before, I guess I'm still here. Okay. We can pass it different initial parameters and we get different results out. It's just passing that all the way through to the end. And we can do the same sort of operation with multiplication, where we're now taking a product starting with our first number across the whole data set. So we'll get those answers there. So one more thing that we want to cover before getting into the feature columns is just to talk a little bit about data set structure. What does this data set object look like internally? It's nice to be able to pass it single integers and very simple numbers like we've shown before. But for TensorFlow, for the dataset object within the TensorFlow ecosystem to be really useful, we want it to be something that can be extensible no matter what the size and shape, no matter what the structure of your dataset. You may have datasets that combine data from multiple sources. We may want to zip data sets together. We may want to pre-process them in any number of ways. So we'll investigate the structure of data sets in the next few cells. So here's a link to the code that actually underlies the data set. I believe that made the same GitHub page that I was looking at before, so we'll not click through that. But every item that a dataset yields is called an element. Each element is the same structure of components. Each element has to have the same structure. And you can have individual components, really can be any different type. And the components can have some kind of a nested structure, as we'll see here soon. They can be tuples, dictionaries, named tuples, ordered dictionaries. Little story here about lists, but you can't use them in data sets. So one useful tool if you're trying to understand a data set that you already have is to look at the property called element spec, and that will tell you what a single element looks like from the data set. Here we've just passed it a list of numbers, scalars. So we're going to get scalar for each element. So the element spec is just going to return this object here that tells us we've got scalars. We can look at the element spec for a few other. Here's a two-dimensional vector, 4 by 10, since we're using from tensor slices, we'll get the 4 as the number of elements yielded in the iterator, and 10 will be the shape of each one. And here's just another example with the less commonly used from tensors, where you just get a single element with everything. So here's another similar example. Dataset 3 is where it starts to get a little bit more interesting. We can actually zip 2 datasets together. So we can take dataset 1 and combine it with dataset 2. We can only do that as long as dataset 1 and dataset 2 are the same length. If dataset 1 and dataset 2 have a different number of elements, so they each yield 4, the iterable that would be created yields 4 elements. We will see later that there's some flexibility regarding datasets, and in fact you can have datasets of infinite length. So in that case, this comparison is not necessary. But for finite datasets, you will get an error if you try to zip datasets that do not have the same length.
Robert, is dataset 2 some kind of a tuple? Is that what it is? There's 2 parts to it?
Yeah, I guess maybe that's why dataset 2 is a from tensor slices, and we have it's a tuple of 2 different things, and this one actually also needs to be the same number of elements in each one.
You sometimes want to do that when you want to package your features and labels, right, in the same representation, so that X and Y's become tuples.
Yeah, that is probably the most common use case for delivering tuples out of your dataset objects.
And then between dataset 2 and dataset 3, 4, which is basically how many records you have, in my mind, how many rows you have in your matrix, is something they share. But then how many columns or how many entries they have, like one has 100, one has 10, that is independent, right? They don't have to match. They only need to match in the first dimension.
So the number of elements, so TensorFlow in the documentation makes a distinction between elements and components, and the elements are each object yielded by a dataset. So for instance, the element here is this tuple consisting of one thing from dataset 1 and one thing from dataset 2. The element in dataset 2 is a different tuple consisting of one scalar from this and one vector of 100 units from this one.
Yeah, but I'm just saying that in dataset 2, if you look at the second component, it's a 4 by 100 entry versus in dataset 1, it was a 4 by 10.
In dataset 1, right. Dataset zip, dataset 1, what do we have? I guess dataset 1 is this from tensors. So I think I may have misspoken earlier. I think when you do a tuple like this, you have to make sure that the numbers of elements match, but you can zip. I'm not sure that they have to match when you zip.
Yeah, I don't think it cares.
Oh, the 4s? Oh, I see.
So the 4s had to match here. You'll get an error if they don't. But here you see dataset 1. We've defined dataset 1 back up here as this from tensors, and it only has one element.
As far as I remember, so the only thing that needs to be matched is the first dimension, that 4, which later becomes the batch dimension, and everything else doesn't matter. You know, they can be different dimensions. and different structures, but the fours need to match it.
So if dataset 1 was 5 by 10, the zip would have worked?
It wouldn't zip, I think.
It wouldn't zip.
Yeah. Or it could, do some weird stuff like the Python zip itself, right? Which sometimes does the shorter of the two.
Truncation.
But yeah. But I would expect TensorFlow wouldn't allow those shortcuts. Sometimes it's too strict, but I think it's a good way. It's a good thing.
So in this case, it's possible that actually the first tensor is broadcast. So
I don't know. Yeah, is it broadcasted? I don't know. Is this a runnable notebook, Robert? Can you just quickly change that 410 to 510?
Quickly
Dataset
change
for
what?
dataset 1.
Dataset 1.
Yeah.
Sure. I may want to rerun everything again after doing that because I'm sure I reused datasets 1 and 2.
Okay, no problem.
Oh, okay. No, we can just run the whole thing again because it's actually a very quick restart and run all. The entire notebook all the way to the bottom should execute in a minute.
So yeah, just change dataset 1 to 5 by 10. Or introduce a new one, dataset 3 or dataset 1B or something.
So let's see. I guess there was really no reason to run restart and run all since I hadn't changed anything yet. So we want to do what? Dataset 1B.
1B, yeah.
Is equal to tf data.
Yep, from tensors. From tensors, yeah.
$510.
Yep. Perfect. And then when you zip it, just zip 1B.
So I'll just put a B here.
Yep.
Yeah, I don't. It's just a single element again from tensors going in there. So what maybe another interesting question though might be, what if we had done from tensor slices, where we'd have 5 elements against 4?
this should break. The first one broadcasted. This should break.
No,
Looks like it handles that.
I mean, you can see from the spec, it's just putting them into the same tensor data set. It's not really adding them or it's not doing any operations between them.
Now, one thing I'll say is that I have not re-executed dataset. I'm sure that dataset 2 got changed somewhere further down in the notebook after this. I probably need to find it somewhere, so we're not even combining it with, like, this 11 here doesn't match anything.
Yeah.
So run it again, right? Dataset 2.
But yeah, I can run this cell again.
And then dataset 3.
I think the extra one is omitted, so it runs all the way to the one that you have, which is 4. You can check the number of elements in dataset 3. Is it 4 or it's 5? How much is it? Because if it's 4, that means that the fifth tensor from dataset 1B is actually missing. Try dataset 3 dot take 4. 5. If there is no 5.
Yeah, we'll try that.
Maybe. Maybe shape, yeah.
Take 4 should be there, but take 5 should be great.
Just need it.
Okay, I'll stand there.
Isn't there a shape attribute as well or method?
Yeah, I can do 4. Let's do 4x comma yz in. That might work. Didn't close it. It does look like it stopped the iterator after 4. So it doesn't give an error, but it did only yield 4 elements.
Can you do dataset 3.shape? Last thing.
So it zips to the shortest, like the Python zip.
That makes sense.
I have seen something with tuples. So if you try to make, let's say you take two lists of different length, it creates a data set only with elements of the shortest. You can try it immediately, just from tensor slices, 2 lists, 1, 2, 3, let's say range 4 and range 5 or something like this. And then you see the data set is actually runs to the shortest. I think that was the
I couldn't catch that.
so if you so because we are dealing now here with tensors, it's very difficult to say what's inside. So if you make two data sets, let's say A and B or something. A is from tensor slices of range, let's say 3. The other is range 4. The B data set is from tensor slices of range one more or a little bit more, and then you zip them, and then we can see exactly what.
Okay, I see where you're going with this. So we can do a very
very simple.
The most trivial example.
Yeah. With just the two lists, 2 ranges here. I think it works also with ranges. There is tensorflow.data.range.
Yeah, there's a range data set as well. I was just going to do it manually because it's so easy to put the code here.
Yeah, the other is one more or with 10s, 10, 20, 10, 11, 12, 13, let's say. And then
It is
to have different numbers to see how the numbers change, because now
right.
Yeah, something like right. And then zip them, and then we can see what happens.
Yeah.
No, directly print X, and then I think X will work directly because it's already.
I think you're right. We can see the actual numbers.
Yeah. Okay. X dot numpy. So convert this to numpy. I think that's going to work.
Well, the 3, 4, 5, it's there already, right?
Yeah. Okay. See, right. Okay. We see, right.
See that? I mean.
Yeah. Right. So.
Just be 1, 4, 2, 5. There's no 6. Okay.
So it pairs them, but the extra ones are ignored. So it takes the shortest.
Cool. Sorry for the divergence, right? We have a lot to cover, so I think we should get going.
So, yeah.
Little live coding never hurt anyone.
Right.
So at this point, there's a number of cells here where we just talked about data set types. I think we had a discussion on this in the last meetup where we discussed some of the differences between tensor slice data set, You can see when you actually look at the types of these things, they're tensor dataset, zip dataset, there's range dataset, batch dataset, whatever operation you can do on a dataset, almost every one of these things, padded batch dataset, prefetch dataset, range dataset, shard dataset, they're almost all these different types defined. And if you're really interested in investigating that, there is some code that I thought I just saw the link to. Here it is. So you can see that this file has more than its fair share of lines. I think it's a 5,000 lines of code here, all describing all this variety of different tensor datasets. But bottom line is that they do all inherit from the original dataset in some kind of hierarchy, dataset adapter v2, I think. And mostly they are views of objects, not so sort of like the distinction between transformation and actions when one is using Spark. You're defining a computation graph in advance, but you're not actually changing anything in memory when you are creating all these different types of data sets. So there are a number of transformations that you can do once you have a data set. You can do a map, you can do a filter. Here, let's see, we're just looking at some NumPy. We mapped an original data set that had these numbers, and we're just able to show how you can apply a very simple unary function to it. Here, this is where I redefined data set 2 to have 11, I guess. So here what we're doing is looking at the filter function. So we have a data set that we're printing out here at first. It's 7 elements and they're nested like so. There's a float out front and then an array of integers behind it. And we can actually define a filter on these objects. So only choose the elements where the first element is, choose the samples where the first element in the tuple is less than 1/2 and the second array starts with a number less than 50. And you can see that it will down select to the only incoming samples that meet that criteria on the fly. So at this point, I would like to turn it back over to David. The first part of the course talks about how to build feature columns, a variety of different types of feature columns that can be passed into data sets. And we'll see some of them, I think, in some of these data sets further down here. But he's got some information to share.
Robert, before you stop sharing, I just was curious, did they show the map function with an actual defined function? Because that's really, really powerful. Like,
with an actual defined function.
Yeah, I think they showed map with a lambda in there, but you can actually...
No, they actually, so I noticed when going through this notebook, there was a little bit of text about transformations and maps and filters, but there was not a single example. So I just wrote these myself.
Oh, you wrote the, okay. Yeah, because that's really powerful. You can just define a generic, Python function and put it in that map as what you're, instead of using like a simple lambda, you can do very, very powerful functions.
Yeah, I think there are examples later down, but where they introduced the concept right here, there was nothing.
Okay, great. Maybe we'll get to it later. Thanks.
One question, Robert, you mentioned something about the different types and look at the code, and you mentioned something about the graph. What was that connection you're trying to make, that they had the same underlying structure but different variety, like slices or maps or hashes?
So I think this goes back to a discussion we had with Vladimir, I think, last week, where he pointed out that all these different types, the tensor slice dataset, tensor dataset, batch dataset, range dataset, they're not really new objects in memory. They're just defined transformations that will happen once the data are actually loaded and processed by a model.
Mm-hmm.
So they're more abstract classes than instantiated objects.
I see.
So, okay, I want to add something about, because I'm struggling with similar problems. I'll start with the map, because that's kind of, so this current map that you currently see, whether you have a function, regular function or a lambda function, this is a sequential map. So this means that it runs in the same thread as the other things that are before and after it. If you set it as a parallel, so there is a command and num parallel calls, I think it's called. It becomes a parallel map, which is, they call it asynchronous function, and it is put in a separate thread. So the data sets that, so this transformation that you have, dataset one.map, and then some function, becomes a new data set. And in one case, when it's without a number of parallel calls, it is called normal map. But if you have number of parallel calls, it becomes a parallel map. So on the computation graph, this has different position. So when you start actually executing it, this data set that you have produced with parallel map can be put on separate threads, kind of replicate it, and then you can parallelize things. So the data set itself is, yes, it's kind of different probably view on the data set. So it's not a, but it carries in its information about its last transformation that you have, whether it's mapped or batched or interleaved, whatever. I don't know exactly how it works. So this is just what I have seen so far. But if you put this in, let's say, PyCharm or something, and you see the variables, you see on every transformation that you make, and every map filter, whatever, you get a different variable, and it is, and then you can map this, and then you can see how this executes when you do this tensor board profiler, and then you can see how things are actually executed in time. So the bottom line is that it is far more, let's say, sophisticated. And the reason why it probably went this way is because the goal is to have a high performance computation. In this specific case, it's a high performance data input. And I am actually trying to understand how it works. That's why I'm in this meeting right now. So
yeah, thanks for sharing that, Vladimir.
Thank you, Robert. Okay, so as Robert was addressing basically how you're bringing in the data and putting it into your data set and the different things you can do with that data set. What I'm going to be looking at is, if you recall, many times you've seen us go through actual data sets and have to do a lot of pre-processing of the data, such as normalization or taking categorical data and converting into different encoding methods to make it into numbers that we can actually use in our models. So many different steps in the pipeline that involve pre-processing. So what we have an option to do in TensorFlow is something called feature columns. And what that does is let us do a lot of that pre-processing that we normally do with sklearn or other libraries. Instead of doing that, we can put it into our model as some early layers in the model that will do that pre-processing to any kind of input. It could be a data set, it could be NumPy arrays, it could be a data frame, anything that our model is going to bring in the correct input format. These feature columns will then do that pre-processing for us. So let's get into that. Here's just an overview on the different type of feature columns, and I'll go through all of these in order here, but in general, you have categorical columns and dense columns that are already your numbers. And there's a special treatment of them called Bucketized Column that you can do. The categorical columns have these different ways of addressing categories, depending on if you've got kind of like a true false type of category, or a lot of different codes that you need a vocabulary for, or maybe something even more sophisticated. On the dense side, you've got those numeric columns, basic indicator columns, and the possibility of embedding columns. And I'll show all these. Since the I guess since the course was developed, they've added a couple of different ones that they don't go through in the course. So I'll mention them, and you can look for them. But there are several ones underneath sequence category now, categorical for when your data is a sequence, and you want to deal with that that pre-processing via the feature columns. They also have a sequence numerical for when you have numerical sequences coming in. And then we'll get into embedding. When you do embedding, you come up with vectors that represent the embeddings. If you have multiple columns that maybe have the same type of categorical values in them, and you can actually just learn one set of embeddings that can be applied across multiple columns. So that's what this shared embeddings is. And so now we'll start to go through these. The first one that we saw underneath the different ones was the idea of a bucketized column. And I just captured some of the work that Lawrence put in some of his videos, and just captured a few things. But here, if we think about if you've got a column that has a bunch of different dates in it, or years in it really, and instead of just having the model have 100 or 200 years worth of possible categories, we can throw those into buckets. And here we're going to say that anything before 1960 is going to be bucket 1, and between 1960 and 1980 is 2, and so forth. And that basically gets represented now as these kind of one-hot encoded vectors that represent the different buckets. And you can of course define your buckets any way you want. So that's one way of quickly reducing the representation. So this is most of these methods that we do are either to get our values into numbers that a model can use, or we're trying to reduce the representation space that's needed to show those, especially in the case of sparse things. So the bucketized column is one approach where we take what could be hundreds of years of different values that now we bucket into 4. And for a lot of models that might work well. You can think about people's age or many different things that you can use buckets for. So that's the bucketized column that can either come from numbers, dense columns, or category, like we showed years, but it could be some other type of collection. The next one we want to look at is when you've got a kind of an identity column, where you've already got numbers that represent some value in a category. And instead of feeding the numbers in, which may or may not have some sort of order to them, or is 55 really that much better than 25? Maybe that's not true, maybe it is true, but if you want to make them basically identities that say you've got 1, 0, 0, kind of hot encoded for them, you can use this categorical identity. He had, in his example, he had done 0, 1, 2, and 3 and mapped them over. And I thought it might be better. It struck me that what if these were speed limits, right? So maybe you're doing some kind of modeling of severity of car crashes or something, and you have this type of data. Maybe this is a useful way to, it's probably not, I probably would stick with the basic values, but it's just an idea of what you can do with identity columns.
So the difference doesn't have to be the same. Is that what you're trying to say here, or?
I'm just trying to say you've got some number values that represent, a unique identity, and you basically one-hot encode them, right? You're remapping them as 1, 0, 0. Does that make sense?
Mm-hmm.
George, that answer? Okay. Yeah. If you don't, please ask me if you don't. All right. So that was the categorical column identity. But what if we've got strings, objects instead of numbers in there? So here's an easy way to do it. Let's suppose we have a vocabulary where we've got these items in a store or whatever, and we want to map them to a category. We can, again, this is kind of a way to do that. You can do this in two fashions. There's a vocabulary approach with a list where you have all your list of things in the code, and I'll show you how it's done. The list of possible values for the category. Or you can do it with a file if you've got a file that has all, but you have to know them ahead of time, or you have to put in a special option for out of vocabulary type of values that you might see that perhaps you have not seen in testing, but then when you go to do your inference, you have something new. So you need a way to handle all that. I'll go through in the code, we'll go through specifically how these are used. I just want to give an overview kind of the different options. We talked about reducing the feature dimensionality. If you've got a lot and you don't want to go and produce these kind of sparse vectors that can get really, really large if you have a lot of values for your category, right? So one approach for reducing that down is hashing. Sometimes you hear this called the hash trick, but here it's the hash column, and you take, suppose you had many more than this, but basically apply the hash to them, and you get, they hash to numbers. You do have the possibility when you have a very large number that you will have some values that will hash to the same, to basically convert to the same hash. And that could be good or it could be bad. If you're lucky, maybe there's a relationship between them and they should be categorized, but it's possible just a hashing algorithm has put them to the same hash just out of chance, and it doesn't really lead you to any more meaning. George already mentioned there's and I'll go back and forth several times here, but there's a nice site that was pointed out by them about, if you don't know a lot about hashing and how hash tables are created, I encourage you to go read this tutorial. It's a really nice overview of that. So that's a nice resource that they gave us. The next thing that we're going to look at is something called cross columns. And if you remember from our feature engineering course that we did on Kaggle, we introduced the concept of interaction features, where different features, we built up interactions between them, usually by some kind of multiplication of the two features. And that gave us a new feature, which actually helped our model out. Mm-hmm. Particularly, it's good for introducing kind of nonlinear effects. So these feature crosses are, come from templates of feature A times template B, feature B, but they can be much more complex with that. You can take multiple columns and have them be a cross. And there's a little thing about here, if you're dealing with Boolean features, you can get a lot of empty values, so you get a lot of sparsity. So it may not be the best approach when you're dealing with a lot of Booleans and bins that might be empty. But this is an easy way to introduce some new feature engineering in there. Again, there's a good resource on this. It's a free course from Google, and he gave the URL for that. And they go through really what feature crosses are if you're not familiar with that. And again, in the notebook, I'll go through the syntax of all this. So just wanted to give a brief overview of these different types of columns first.
Yeah, I remember in the notebook, it mentioned something that internally, not every combination is computed, but maybe the most popular combinations or something like that, like a very small subset is actually crossed and calculated.
Yeah, it's actually, they go into a little more detail, but it's actually backed by a hash. So that's why sometimes, yeah. So you get a little more, but they go into detail on that.
Yeah, I thought that was that was the most compelling use case they gave for the hashed columns.
Right. Okay, so we've kind of covered all the categorical possibilities, the bucketized. Just real quick, I'll show the different types of sequence. You can see over here on the left the different list of all these different approaches. Basically everything you can do, like the identity and the vocabulary file, you can use that when you're building sequences with a bunch of different columns. So that's very useful. Or you can do it with numeric, with a sequence numeric. He doesn't go over this, and I'm not going to go in detail, but it's pretty straightforward if you read through the documentation. So back to the. All right, so let's go and look over here at numeric, indicator, and embedding. And the most useful one, I think, that we're going to go the deepest into is probably embedding. This is very useful when you've got a large number of values or different possible values in your category. So a lot of different strings. He shows 4 here, but there could be literally thousands in some situations, depending on what your data holds. The first thing you have to do is convert these into a mapping to numbers. And you can use any of the prior categorical column methods that we were showing. So you could use hashes, you could use a vocabulary list or vocabulary file to get these numbers. But the interesting thing is the next step we can do is feed this into an embedding column where we have a lookup table showing, in this case, he did 3 dimensions, but you can set this as many dimensions you want to, of embedding vectors. And these are actually learned values that when maybe this one and this one are compared to each other, the model can learn there's some meaning more than just numbers. There's actually relations between these numbers now. So this, instead of just giving us a straight kind of categorical column where we had a hash or we had random numbers that we got from a vocabulary list, we're actually going to derive some meaning via an embedding approach. And if you're familiar with embedding that's used in natural language processing, you already have a heads up on what's going on here. So this is how it's done, and I'll go through the syntax of it in much more detail in a few minutes when we get into the notebook, because it is kind of confusing when you first see it. One thing he pointed out that I hadn't heard before, and I thought was a really neat thing, he basically said there's a rule of thumb that when you're deciding, this is the syntax for a embedding column. So you're telling it what column is it we're going to use and how many dimensions. In other words, how many of those, how big are vectors that have the embeddings in them going to be. And his rule of thumb was, when you're choosing this, it's wise to choose the number of unique values in your feature. So, the number of categories you have in that feature times 0.25. So basically take a fourth, or sorry, not time, but to the power of the 0.25. So this will give you a starting for this. You can adjust this. Obviously, this is a hyperparameter, but it's a good rule of thumb for when you're choosing this that I had never encountered, but I'm going to try it. So
I thought that was interesting, because when you compare it to the obvious example that you gave with word embeddings,
yeah,
a typical dictionary size might be 10,000, and 10,000 to the fourth root of 10,000 is 10, and almost always words are embedded in dimensions higher than 10.
Higher than 10, yeah.
So, and then I was thinking about it further, and I thought, well, maybe the reason that we can get away with words being embedded in much higher dimensions is that often they're just trained on enormous data sets, right?
Right.
So we have a corpus of Wikipedia and the internet that can give us a model that can get pretty good embeddings over a large number of dimensions, whereas maybe we'll really overfit for a small data set, such as the ones that we'd actually be using these methods on.
That may be. Like I said, I've never seen this before, so I'm not really sure. I mean, it must be something that he's had some experience with, or someone that he's worked with has found it to be, be effective. But I did mention numeric columns. He didn't really go over much in this. It's in the notebook, so he talks about it there some, but there's some nice possible parameters you can use that I didn't see him cover. But one of them is you can put a normalizer function in here that all these numeric values would be normalized via that. And you can define that. They give some in the manual. They give some overview of how you do that. But so this is what we do a lot of times. You see us normalizing the values and all that. So here it is being done again inside of this column, numeric column. So I just want to throw that out there. So I'm going to move now to the notebook. I did want to show this natural language processing in TensorFlow. It's part of the I guess now they call it their certificate program for TensorFlow developer. But this is what he was talking about in this course. They go through the embeddings a lot more for a deeper understanding of what's going on in that. So I just want to point that out.
Is this what we covered in the TensorFlow in practice specialization?
Yeah, this is what we did. Yeah. So I'm going to move on to the notebook, and a couple of interesting things happened in this notebook. Here's the GitHub for the notebook. If you notice in here, this is a data set that has to do with heart data in terms of cardiac problems from the Cleveland Clinic, and it goes into how that is. But if you go to run this on Collab, it actually takes you to a different data set, which is, I think, where is it? It takes you to here, which is the same title, but now we're going to deal with a pet finder data set from, I believe it comes from Kaggle. That's completely different than heart data, but it actually covers throughout the very same type of things, just with a different data set. So I'll talk about both of these. So if we go to the one that was on GitHub, here I loaded it up into Collab and ran it. The first thing we're gonna do is look at this data set. It's comes from the UCI Machine Learning Archive, where they have a lot of different data sets. It's the one about heart disease. And it has 4 different data sets, one from Cleveland, one from Hungary, Switzerland, and California. The most popular one that's used in almost all the research papers on this and examples would be the Cleveland data. Apparently the Hungary and Switzerland and Long Beach have a lot of issues with the data. It's incomplete and not very useful. So the Cleveland one is the one we use. It is not a large data set. You actually only have 303 rows. It's very small data set, but it's very useful for basic examples like this. We're only going to use out of the, I believe there are, let's see, I can see 76 different fields, not of all of which are going to be populated or fully populated. But we're going to take 14 fields from there, one of which is going to be this number, which is going to be our predicted attribute. And the number represents a diagnosis of heart disease. And it's a little bit different in the Cleveland. It's not just 0, 1, it's 0, 1, 2, 3, 4. There's 5 values for it. So that's what we're going to work with. But then we have some other values in here, such as the age of the patient, male or female, level of chest pain, things like cholesterol, resting ECG, and some other things like peak rate of the heart, different measurements. So, and they're all explained in detail as to what they are. THAL is one we're going to look at. So I just want to show that. That is 51. So this is probably way too small for you guys. I apologize. But THAL has a value. It has to do with have they had previous issues with like a heart valve or other defects in the heart. And the values there are 3 is equal to normal, 6 is equal to fixed defects. They've had surgery. 7 is a defect that could be reversible. I'm not a doctor, so I can't tell you about everything, but that's the basic overview of the data set. Is this too small? I'm just gonna try to increase it a little bit.
Perfect, yeah.
A little better?
Yep.
Okay. So again, here are those columns, the description of them. It's a good mixture of numerical and categorical columns. A lot of them are already, except for maybe thal, which in this case, this is not actually true. This is also an integer. Everything's already a number, but I'm going to do some stuff to deal with it. He's going to get sklearn because he's going to use it to split the data set. So we've seen train test split before be used, but we're not going to do any of the pre-processing with sklearn. We're going to use our feature columns to do all the pre-processing. So we're importing the feature columns, the keras layers, and as I mentioned, the train test split. So the first thing that I had to do to actually get this to run, and this may be why they're using all the different, when you click on it, it's actually using that pet finder data set. This actually throws an error that apparently doesn't exist here anymore. So I had to go and get it directly from this UCI archive. So as you see, I got the Cleveland data. It comes without column names, but they're very straightforward what they are. So you can put them in, and you just place them in here. So I'm reading it into a data frame, and here's an example of the data. As I mentioned, everything's already a number. So, and here's our target data. As I mentioned, the target has values 0 through 4, most of which is no heart disease. So it's an imbalanced data set. We're not going to talk about, we're not trying to get the best results here. So we're just going to use this as an example, but you might want to consider the imbalance if you were trying to get the best result. Everything's a number except for CA and THAL, and I'll show why that is. When I looked at the value counts, there are actually a few of these that are not defined. They just have a question mark in there. So I'm actually going to throw those out and only select the rows that have that in it, that have the 0 through 3 for CA. The same thing is going to, and then of course I had to convert it back to float. The same thing happens in THAL. We've got a couple of that rows there where the value's not present. Obviously we could do imputation or some other approach to try to resolve this, but for this example, I just threw those out so we won't have to deal with the problem. So I'm just cleaning up some issues. This is where I had to do some of the manual work, pre-processing. I could not do this with feature columns. So, but to show some of the feature columns, such as the categorical things, I needed to convert these back to the actual categories so that we can see how to apply feature columns. So I just took these and put them back to what they represent. So now you'll see we've got another imbalance, but we got some idea of these different ones available to us. We're gonna take 20% of the data set and define it as set it aside for testing, and then from the 80% that's left, we're gonna take another 20% of that for validation. Just wanted to split it up really easily. You can see it's very small set, so we wouldn't expect a lot here. But as Robert mentioned, we're gonna now read these with from tensor slices, and we're gonna read in a dictionary representation of the data frame, and labels. Our labels, we're just going to pop the target column off as the labels and read that in. We're going to go ahead and do some processing on the data set. We're going to shuffle that value and batch it. Batch size is 32, and we're going to shuffle it's true. So here we're going to go ahead and just so I can show you some of the output after you apply the feature columns, we're going to do a very small batch. So we're just going to look, just for right now, we're going to just do 5. So again, we're just applying this. We don't shuffle the validation and test data set. There's really no reason to do that. Here's the input pipeline. I'm just going to take the first batch and show you that. So here's the features that are in the batch. I can't remember. One of the values for the first column is age, and you can see there's different ages of the patients, and then different values for the target. So here we can see 0, 1, 4, 2. We don't have a 3 in this part, but there's probably a 3s in there. So now we're going to show. We're going to write a little helper feature to be able to show these feature columns. This is just for demonstration, but we're gonna use an example batch, which would be the next iteration of this training data set, and we're gonna have this feature called demo. So we're gonna pass in a feature column, which is we're gonna define those later, and for when we pass in the feature column, we're gonna use a layer in Keras called dense features, and in that place you can put your feature column in there, and you get a layer out of this. And we're going to print that layer with this example batch that we got before and show the actual values that come out of that. So our input's going to be just the regular values that we saw above for the data set. And then we're going to apply our feature column and see how it transforms that particular column of data.
David, question:
yeah.
This dense feature, how is it different than a dense layer? Is it maybe like an embedding or a hash function? Like, what does it do in the background? I didn't see that in this notebook.
Yeah, so it allows you to take see how to explain it. Your outcome is always going to be it's going to be dense layers, but it's what's the best way? We can look at it really quick. Let me just go over here.
Is compacting the representation somehow?
I honestly, I just have used this so much, but I don't ever really think about what it does. So yeah, you're passing in feature columns, which can be just the feature columns can be all the different ones. Trying to think of the output. The output of it is.
Can you scroll up here? Generally, single example in training data is described with feature columns. Should be converted to single tensor. Can be called multiple times.
Yeah.
So it is trainable as well. Interesting.
Oh yeah, yeah. Well, you would want it to be trainable, right?
So is it like an actual dense layer in Keras?
We can probably print it out, but
is it taking multiple column types, data types, and returning a single tensor that has one D type?
I think that's right. Yeah.
Like int or something, or float? What is it?
Tell me what it returns, but I'm pretty sure it's returning that.
Okay, we can look at it offline. Thank you.
We can also maybe print out a model summary and take a look at it.
Right.
Just remind me when we get there.
Yeah, this demo method, it's so deceptively simple, but has a lot going on here.
Right.
Because you're going to see later on when you do different things. I had a hard time figuring out how does your transformation connect to the data set, and I'll come back to it later. But
Okay.
I didn't see it initially.
All right. So the first one we're going to show is a numeric column. And the first thing you're doing is putting, this is called a key, but basically it's the column name. So we're going to look at age, and we're going to pass this defined numeric column into our demo and print out the layer, the feature layer that we get from that. So if you recall, our first 5 ages in our example were here are the values. So this is just a very straightforward tensor that it produces, and nothing too complex here, because we didn't define any normalization function or anything, but we could have, and that would produce a normalized set of numbers for us. We mentioned bucketized columns. This is the syntax for that. You're going to pass in the column that you're going to, the key again that you're going to try to do this, and you're going to define those boundaries as a list of numbers. So here's these ages of, up to 18, up to 25, up to 30, all the way through 65 of us. So we're going to now, when we print that, we're going to get each one of these samples now becomes a list of the buckets and which bucket it's in, right? So that's what's going on here. So these ages, if you recall, 53 was the youngest, 65 was the largest. So here I think, oh wait, was 53 the youngest? No, 46, sorry, 46 was the youngest. So 46 went probably into here. And so it's here, and then the oldest was the 65, which was the last boundary we had, and that's this value here. So that's the use of buckets. Categorical columns, they give an example for a list. So here's the syntax for that, and we're going to use this with that thal that I said, and so now you see why I had to convert it back to the actual strings. They should be the same for the vocabulary list here. They should match up. Mm-hmm. And when we print that, we're going to take this category column that we produced, and we're going to put it into an indicator column. So he's really showing 2 different types of columns here at once. You often take that and do that. So here we're just going to one-hot encode these categories. There's only 3 of them, so you can see they're being written out that way. I wanted to show, let's see, I have that I think over here. Yeah, so we just saw how it's being done with a vocabulary list in the example, but I wanted to show the vocabulary file method. It's very similar. There's a couple of examples where you have the key again, which is, but you didn't tell it where the file is that you have your categories listed there, and how you need to tell it how big that is. These files are just, each category is on a separate line, and it just reads down to the size that you put here. If there are 100 in there, it's only still going to read the first 51. There's a couple other options that you have here. If you think you might have ones that you can specify out of vocabulary buckets that you can have things, so you can different way handle things that aren't in your initial file. So if you don't have those values in your file for a category and your model comes across those, you can have it either use these type of buckets to handle it, or you can define a default value, and it'll like, for instance, you might have -1, as being a default value. If you put none for this and you don't use this, then it'll automatically use -1, but that's just an example. So different ways to handle that. Let me go on to back. Any questions on what's going on there? It's not too hard, but it's a lot of times I see these category columns being used then to go into something else, like an indicator column or an embedding column, and we'll show that next on the embedding column. So, as again I mentioned, in case up here we've got only 3 of these values, but what if we had thousands of different values for this particular feature? Well, you know, we don't want to produce vectors that are 1,000 dimensions for all these. We'll have a lot of, you know, really hard model, I mean, a hard data set for a model to handle. There'd be so much sparsity, very slow to converge. So one way to handle that is embedding columns. So we're going to try to learn something about relationships between these possible categories. And here's that syntax. I talked a little about embedding, but here's the syntax for that. We're going to take that category column that we used above. So where we introduce this here with a vocabulary list, we're going to then put that into an embedding column where we're going to use dimension of 8. Now he's not using his rule of thumb here, but we're just doing this so we have something to show.
Right.
It's kind of, you would never do this for something that only has 3 values, possible values, right? So this is just for a demo, but when you do that, you print out these embeddings that you get from that. And these will be learned, but these are initialized in this fashion at the beginning. He didn't go over this, but you have the option when you're doing this to, let's see, define your initializer. There's a default here that uses the truncated normal initializer, which has a mean of 0 and a standard deviation is the square root, 1 over the square root of that embedding dimension that we specified. So that's where these initial values here are coming from. Does that make sense? But that can be defined. You can change that to you know, you can define this differently if you find there's value in using a different initialization. We have an example of the syntax for hashed feature columns. Again, we need to feed in this a categorical. So here's our thal again, just the basic one. And we're going to give it a bucket size, a ludicrous size of 1,000. And they're going to print that out. So these values across here represent 1,000 values of the hashes for those columns. Here it makes no sense because it's 3, but if you had like, you know, 5,000 of these and you want to hash it down, you would reduce your dimensions down to something like 1,000. It's still a very large number. I wouldn't recommend doing that.
1,000 does decrease your probability of a collision significantly.
Yeah, it's a crazy number, but yeah. I wanted to show real values in here, so I did this again with 4.
Mm-hmm.
And if you remember, we had, so here now we can actually see, you know, some hashes that are coming out, so different values that are coming out. So I just wanted to show that this is actually functional and working. We talked about feature crosses and you know, a cross column. It's just when you take multiple columns within your data set, these features, and you're going to cross them. Here we did this with the age buckets that we created earlier, which is a bucketized column, and our categorical column that we produced with the thal values. Again, he's using a giant example because this does behind the scenes, as I think George and I mentioned, that it does use a hash in the background as part of this. And when you print it out, you don't see anything in there because it's so large. So I went again and I changed it to a much smaller size so that we can see that we're actually getting some values in here for our hash column. So this is a, you know, a featured engineering type of creating a brand new feature that didn't exist in our data. All right, so now we're going to kind of look at how to use these. Instead of just doing demo, we're going to use them in our real data and choose which ones to do it with. The first ones we're going to go through. So we're going to create a list of different feature columns. And the first part of our list that we're going to build up and append to this list is numeric columns. So we're going to do this for each one of these columns in our data set. And we're going to add each one of these into this feature columns list. We're going to do the age buckets. We're going to do this with the bucketized values for that again. We saw that before. We're going to actually use that in our real model. The indicator column, we're going to use that with thou. So with these vocabulary list here, we're going to create an indicator column. It's like a one-hot column for those. We're also going to take thou though and try to pull out if there's any relation between those different categories, if there's any meaning between them, not just whether they're present or not. The one-hot encoding is kind of telling us, is it present or not? But this is going to say, is there any type of relation between those possible values, and do we get any more meaning from that predictive power? So here we're going to take our thou and produce an embedding. Note that this thou is the one it's not our original one. It's actually this feature column that we're feeding into here. So that's important. I think if I had written this, I would have renamed this to thou_cat or something to tell me, what I'm doing. And then we're going to create a cross column. This is exactly what we did in the example with a rather large bucket size, but regardless, here's what we're doing. So this is just for representative. We're not trying to get the best results here. As we talked about before, we need to create a Keras layer where all these columns are put in, and we take our list of those different feature columns and we create a feature layer from that. Earlier, we're using a batch size of 5 for demoing the effect of all those features. But now we want to create a real pipeline with a larger batch size. So we're going to make our batch size 32 and reset recreate our data sets with this type of batch size. Here's our model. It's just a sequential model. The very first layer is the feature layer. If you think about what these are really doing, they're doing the pre-processing of the input data so that we can use it in our later parts of our model. And it's a very simple model, just some dense layers. And I think maybe in his original one, he had changed the diagnosis of the target. So it was a 0 and 1. You had heart disease or you didn't. But in our value, that number has values 0 through 4. So I just changed this over to a softmax type calculation. And that also meant that I had to change it from binary cross interview to just a sparse categorical cross interview. I did, just for fun, I think he was doing 5 epochs. I changed it to 500. I put an early stopping in there so we wouldn't have to go 500 once we got the vow loss was no longer changing after 9 iterations. And I'm going to restore the best weights from the model. We just went ahead and ran that. You can see it's converging, not to a great number. We didn't try to get the best value here, but when we print out the accuracy on the test set, we're getting about 53% accuracy. So, so this is an example of this. You could apply this to a much more complex type of value. Now, any questions on this notebook before I go to the other one real quick?
No, but can I share something on my end that I think it's useful to understand? At least for me, it took me a while to understand that these transformations. I can share my screen.
Okay. Go ahead.
Thank you. So when you define this training example at the very beginning, and when you define this demo method, I'm just printing here what is this object that we are passing this feature column, as well as what is this feature layer that we are creating after this dense feature. So a little bit more. So for example, when we create this feature column, numeric column age, and we call demo age, this is a numeric column. So this first print here, it's recognizing that age is a numeric column because this is how we define it here. Yeah. It doesn't have any data. That's what I gathered. It doesn't have any data. It just has a key called age that later will be used in your actual data. And where is it used? That connection of the transformation with the data happens right here at the very end, where you are calling your layer to the example batch, which contains your actual data. And your actual data has a key called age, and this transformation then takes effect. But these are basically like blueprints for me, or class definitions, where you're not really doing anything, you're just defining how you will do it. And then when you call the method, this is where you meet the actual data.
Yeah, if you've used a lot of like NLP models like BERT and all those, you'll define like this pre-processing encoding function,
right?
And then it doesn't really get called until the model, to those layers are being used. So it's a very similar type of thing. You can actually call it on some text and output do what they're doing here. Output what's the encoding look like, right? So it's a very similar concept.
Similar for bucketized column, you can see it has source column, default value, boundaries, normalize a function. So it has a lot of content built to it that you don't get to see. For instance, feature, indicator column, embedding column, dimensions, combiner, initializer, and hashed as well, and crossed.
I have a question.
Mhm.
So I have used the Keras preprocessing layers in the past, and they do some of the same preprocessing steps. The bucketizing, normalizing, and embedding, all of that. It just becomes part of the model. So you actually declare them as layers in your model. Save them; they become part of your model.
Can you hold on to that a second, Dimitri?
Sure. Yeah.
I got some slides to cover that.
Oh, yeah, great. So my question is, do these feature columns, do they become part of the model? So if you save model, are they?
Yes, they do
Okay.
become part of the model. Mm-hmm.
Okay. This is what kind of you were doing here, right, David? This is where you're explaining, or you do all the pre-processing, and then you use it in your model here.
Yeah, it's put into the model as part of the model. And when I should have done model summary, but yeah, it'll be in there.
Right. So this is where it's using your actual data, then all this pre-processing when you do the compile probably or the fit.
Yeah.
Cool.
David, and just maybe getting ahead, but which approach are there pros and cons in feature columns versus preprocessing layers?
I think there are, and that'll be clear in a second.
Oh, cool.
Psychic.
Of the excitement.
Yeah.
It's just so content heavy that any excitement for me I'm going to cling on to it.
Yeah. Okay, so that is the GitHub version of this notebook that is talked about in some of the videos, but if you clicked on the actual link to the collab from this GitHub, it would take you over to this notebook, which I mentioned before uses the PepFinder data set. More than that, it has a very important statement right here. If you are starting a new project to classify structured data, we recommend you use pre-processing layers, which is exactly what Dimitri is referring to. So here's where that points to. It's a different tutorial, and it basically now you can do almost everything we just showed you with feature columns is now done with pre-processing layers that are defined as part of your model. You don't have to do all that feature column stuff, but you get like a normalizing layer, which is the same as like what the numeric column did with the feature columns, and it does that normalization for you. You can have, so here's an output from that. Those categorical columns, so they now have a couple different ones, like the string lookup or integer lookups. They have a different one for encoding so encoding those things. Very different names, but essentially do the same kind of stuff that we saw before. We can do everything now that we did before with all these different types of layers. So I'm not going to go through this, but I'm just going to say this is the modern, the new approach that they're pushing. It is interesting to note that I think it's up here.
So is this in your approach? Is that what you're saying? This is in your.
This is the new approach that replaces all the feature columns.
And that's under what?
that I just showed you. Yeah.
Right, and that's under layer.
But the one thing it is still included under the experimental libraries in the layers and Keras. But I think they fully intend to push this into non-experimental approach.
It didn't take very long for the course to become obsolete.
Yeah, it's really simple. Here's some of those categorical crossing. This is we saw that the crossing layers, the encoding, buckets, right, hashing, normalization. All these are there. So
yeah, well, one thing just to add to one convenient thing they have is you can clearly fit on your training data, and they call it adapt. The method is called adapt.
Yeah,
like if you do a normalization, you adapt.
They do it. Yeah, they do it in the normalization one. I'll quickly go to that. So,
what is this adapt? Is that a different version of fit?
So you know how you do a lot of encoders and stuff. You do a fit first, and then the transformation rate.
Yeah.
So you're doing that here with this normalization layer. You're doing the adapt, as Dimitri was mentioning. So
it's like fit and transform in one. Is that what it is?
No, you fit. The adapt is fitting.
Yeah.
But you fit on only the train data set, right? So you keep, and so the same thing goes with all kinds of defining the size of the vocabulary, like when you do categorical encoding.
Yeah, you use the.
You may not know what's coming in the production sort of test set, but you fit on the train set, and there's the same adapt method is used. It's basically like fit in scikit-learn. So.
Yeah.
Is it true to say that there are things you can do here that you cannot do in numerical columns or the other way around?
Here they do.
Feature columns, or are they pretty much complementary or coincide in terms of capabilities?
It appears they're very much just alike. The only thing I did notice is that I mentioned that with feature columns they have some support for sequences.
Oh yeah.
And there's nothing like that yet here in this in these layers, in these pre-processing layers. So they don't have anything like that yet. So if you need that, then maybe the feature columns are. But of course, that's that they didn't cover that in the course. But.
Do you have embedding as well here?
Yes, it's this categorical encoding stuff.
Okay.
Yeah, some of that.
Cool.
You can do the hashing and all those things.
Nice.
All right. Well, that was. Any questions on feature columns? Now that I've shown you don't need them, but no, there's still value, but yeah, it's.
That was great. So the course doesn't even mention pre-processing layers, right? Just the collab.
Just the top of the collab where they put a note in there that if you're starting from scratch, please don't use feature columns.
Right.
Do the layers, the pre-processing layers. The just from a practical standpoint, the encoding of the embedding of examples for categorical features, I have found to be extremely valuable in certain cases. I mean, getting better results than any other way of handling them and using them. If you've got some kind of relationship. The only thing I could think that might be more useful is if you had like a dictionary for every value in that category, some like paragraph explaining what that value means, and you use that to somehow do your embedding, you would probably get a more complete relation. but I've never
Yeah.
done that. But
Can you repeat your first statement? Sorry, I missed it. What were you saying was extremely powerful?
so the idea that when you have a very large number of values for a category,
Oh,
right? It could be, suppose you're studying like arrest records, and they have like all these crime legal parts, violate, terms for each violation, right? There must be thousands, right? Because there's so many laws, right? So, but instead of just kind of like one hot encoding them or trying to hash them or bucketize them or something, you said, well, let's learn if there's a meaning between the values. Maybe it learns that all the ones that start with D are related to vehicle operation, and the ones that start with K are related to drug violations or something. So it develops some meaning in code, and you can, and in certain scenarios that could really affect your ability to do an accurate prediction, right? It can really improve your model.
yeah. This is where your embedding layer is trainable, basically, right? And your
yeah,
the way you transform
embedding
your input is being shaped by the training process. It's trying to find a good representation of your input so that it can solve the fitting challenge.
Yeah.
Interesting. Are these the two notebooks that you wanted to cover with us, Robert and David? Wasn't there a longer one?
Robert has a lot more to go. Okay. He has a lot more.
I was about to say. Oh, I knew there was a long one.
What'd you cover? Like the first?
I was like, oh man,
how much percent? How percent? What's the percent?
Oh yeah, we're nowhere near through that one.
Yeah. So what do you think?
Break
point or?
Here.
Yeah, it's up to you. Should we stop here? Should we keep going over? Are you good with energy?
So I'm okay with energy. So what I wanted to do was lay out the data set, kind of get everybody on the same page regarding the basics. The rest of this notebook is just kind of a greatest hits of how do you process all sorts of different types of data. Lawrence covers it in a 4-minute screencast, this entire notebook in the course.
Yeah, it's amazing.
And he really just, he kind of pages down through it real fast and just skips to a few things that he wanted to say. So it's up to you. We can go through it pretty quickly just to point out this is where you look if you wanted to use a certain type of data, or we can do it in more detail next week. I'm fine either way.
I'd say since we're getting close to the 2-hour limit, I'd love to pause here. Maybe we can park it for next week. But maybe can you give us a small preview what to expect?
Sure. And just to expand on that, what you just said too, week 4 is also a really long week as well. So it might make sense to even take 3 weeks between the 2 weeks.
Sure.
We'll see. We'll see once we actually go through all the content.
Yeah.
Between week 4. Sure. So let me actually open up this table of contents. So we did the basic mechanics and dataset structure. What happened?
Mm-hmm.
And now we have reading input data. This is how to read, consume data from NumPy arrays and turn them into data sets. Python generators turn them into data sets. TF record, we get some methods for text data, consuming CSV data, and then sets of files here is really about zipping things together, or in some cases shards. I can't remember if the shards bit was in the TF record or if it was down here. Then there's a section on batching, which is pretty basic. They show some examples of situations where your batches don't all end up the same size. So you may want to, or your elements that result from a single call to take one element out of your iterator don't necessarily give you the same size. So there's some padding that you can do if necessary. Some basic stuff on training workflows. This is more about transformations. I think certainly the shuffling part that was kind of interesting. And then a lot of pre-processing, each of which is somewhat specific to different types of data sets that we're looking at. We have decoding image data and resizing it, some arbitrary Python functions in case what you need isn't native to TensorFlow. There are ways around that. There are also disadvantages to that, which they describe. Protocol buffers, time series windowing is, we actually covered this somewhat in the bike share bit as well. They kind of refer back to the same notebook that we looked at there. And then some useful methods to know for resampling. And that's pretty much it. There's a little bit of checkpointing at the end, but it's really, I wouldn't say it's the most terribly coherent notebook. It's just a lot of different stuff thrown at you.
Right. Perfect. Appreciate the layout that gives us something to look forward to next week. Yeah, there's a lot of content here, so I'd rather focus an entire session to it. Yeah, and if we even have to move week 4 to postpone it, I'm perfectly fine with that. Cool.
I just want to add that I have gone through this twice, through this notebook twice, and I still don't understand it.
It's a learning process. Epochs equals 3 will be the right one.
Bring your questions. Yeah, bring your questions.
2 more epochs.
Yeah, I think this week of the course has diverged from many of the previous weeks in the sense that it seems like it was, the idea here was to showcase so many of the capabilities of TensorFlow. And because TensorFlow has a lot of capabilities, there's a lot to throw into this week. And then because of that, it just ends up being a firestorm of information, and it's not clear how to mentally get your head around the mix. I think there may have not been as much thought put into how to tie it all together this week as compared to some of the other weeks in the course.
I think the course developers have done such an excellent job in introducing a concept, then looking at a data set, looking at a model, and explaining it to us, versus here, there's this plethora of things you can do, but there's not one data set where all of these concepts apply. And it doesn't make sense for them to do a demo basically for each one of these applications. It would have just gone too long.
Yeah, so what you end up with is this, you're flitting from one data set to another in each of these sections. And there's links. In many cases, there's a lot of broken links in this notebook as well. If you're viewing it on GitHub, I did mention down in here, where was it? Right here. So there's a lot of links in here that are broken that go to. Can you see the bar that pops up at the bottom with the URL target?
Yes.
It says collab research google.com tutorials load data tf.record.ipynb.
Yeah.
And then the fixed link, the actual correct place that we should be going to, is the GitHub version of this same tutorial. So it just has a different starter URL. And this is one example of many links in this notebook that should probably be modified in this way. I didn't replace all of them, but yeah, if you want to go through this on your own, you'll find that you'll want to have a lot of broken links to deal with.
So is it broken or is it outdated?
It just gives you a 403 or something.
Yeah, it doesn't take you to the. It's broken.
Yeah.
Nice.
But if you do visit the fixed links, I would say that these sources, for each one of these given data types, these sources are going to be more comprehensive than this notebook that we're looking at.
Right. And I haven't done week 4, but is week 4 completely different than what we've seen so far?
I haven't started week 4 yet either.
So week 4 we'll get into a lot of performance of the data pipeline, right? So how to optimize your speed of your data. One thing that's really important when you're using these is the ability to feed, if you're using a GPU or a TPU, to feed it, fast enough, and so that it stays busy, and so they go through that a lot.
Also in week 4, there's a whole section now marked optional, but I understand it may not have been optional a year ago.
Yeah.
On publishing your data sets.
Right. To tfds. Yeah.
Yeah. What's now called week 4 used to be week 3 on performance and week 4 on publish.
So, I have gone through week 4. It is mainly about how to speed things up, how to get this parallelization. I wouldn't say there is a lot of information, but what it is, it's hard to understand unless you know TensorFlow, how TensorFlow works under the hood. That's kind of my rough experience. So in some, okay, let's get to there, but it's
we'll get there.
That's kind of my feedback.
Another question. Robert, you showed us all this cool input data, right? NumPy, Python, record, text, CSV, sets of files. Does anybody know if there's a way to read from like online, maybe URLs or like Google storage buckets or S3 buckets or things like that? Or everything here, you have to physically download the data into your machine and then read it?
So there are ways to do that. But I don't think it's shown here at all. No.
Okay. So you have a large data set, right? And you want to bring it a few records at a time from an online location. And you don't want to export or download it locally first.
So I think there's a way to do that in TF records also, but I've forgotten how to do it. But yeah,
right, like in pandas, right? Like you have read CSV, and the CSV could be a local CSV or it could be a URL, or read JSON. It could be any. Could be local.
Right. But what you're talking about, like only bring it down when you need it and stuff. There's some advanced stuff.
And there's no performance. I was hoping they would compare the feature columns versus pre-processing layers to see which one performs best, but that's not happening.
I guess the pre-processing is new, right?
Is newer, I guess, but I was hoping it would be a. I'm hoping there's a link somewhere out there, a blog that kind of compares the performance.
So what Keras had that on their site for many months, I believe. I think it's just TensorFlow is lagging, integrating the Keras stuff.
Yeah, they've been bringing it in pretty fast, but the one advantage I will point out, if you think about it, the pre-processing layers, whether you do the feature columns or the TensorFlow Keras pre-processing layers, every time you input data during the training, during the epoch, it gets pre-processed again, right?
Mm-hmm.
It happens each epoch, it's done again. But the one advantage with the pre-processing layers I've seen described is you can put it via, I think you have to do it via a dataset map. You can use those layers as a function to the pre-processing as part of your definition of your data set, or your setup of your data set, so that it's only done once at the beginning. So if that's desirable to you, obviously if you're doing something like pre-processing random rotation of images, you want to do that each time you come through. You'd want it to get a different one, right? But for some of these other things, you may, like normalization, you only want to do that really one time. The caveat I'll throw out there is that when you do inference, you'd rather have all that stuff done when it comes into the model, so that you don't have any special treatment of the data coming in for production prediction, right? You'd rather your model just handle the data and do the normalization inside the model and do all the other pre-processing. So for training, it's maybe good to do it once before you start the training. But if you're going to use this, in a production, then sometimes it's much better to have it be part of the model.
Especially for structured data, right? Where probably the pre-processing is the same. Yeah, you want to do it once. You don't want to do it epochs number of times. Your epochs could be 100, right? You don't want to do it 100 times.
Yeah, I mean, structured data is pretty fast usually, but
Yeah,
maybe with embedding, like an embedding situation where you have a very large dimensions, then it gets slower. Yeah.
Well, there's no point in repeating, right? I mean, it's the exact same operation.
Yeah.
So if you want to do it once, what was the approach you mentioned, David? You do it as
so with those pre-processing layers, there's a way to use them in the when you're defining your data set. So I think you have to use like a map function to do it.
Got it.
And they become a function that
it's,
so that basically everything in your data set goes through those pre-processing layers one time.
So it's intelligent enough to figure out that even if you're doing multiple epochs, it will just do it once and maybe cache it somewhere.
Yeah, depending on how you set up your data set.
Interesting. Should do a session on pre-processing layers, I think.
Dimitri, you can do that one. Yeah.
Cool.
He's good.
Yeah, I could volunteer. Absolutely. Yeah.
Please.
That's an interesting question, actually. So I didn't think about that. So even a simple normalization, if you do like 200 epochs, it's actually fitting the data 200 times. So that's a very good.
Well,
yeah.
Maybe not, because it's doing the transform every time, right? Because you do your adapt one time when you define the layer, I believe.
Well, you build the computational graph once, but then, each epoch, it feeds, the raw data through the graph and adapts it, iteratively. And so, it keeps adapting on the same data, which it shouldn't have basically.
Okay, so we'll do it every time. Okay.
So it doesn't save that normalization from the first time?
I haven't come across anything that says like, it only works for one epoch and then it stops. So it seems to be just ingesting every batch and
the reason being because
updating
a layer above it might have changed the data, right? Mm-hmm. So you want to apply it again, right? So
its epoch is agnostic based. You're starting from scratch with each epoch. You're ignoring whatever happened before.
It pre-processes it again and again and again. Yeah.
You also reading from an infinite stream or something, or online algorithm where you just you're getting new data all the time, so you would want to do that?
I mean, I understand both scenarios. I just want to know if there's a way to pre-process once, or do you always pre-process on each epoch? I'm just curious.
But I think the thing that David mentioned, so it may not be as time consuming to do that, 200 times during training. Training is a separate thing, right? But then inference time, the fact that you have everything already fitted as part of your model, and then whatever comes your way, you have just the platform and everything agnostic thing that knows how to process your data. I think that's the biggest value we get from this.
I get that, yeah.
A great example is like rescaling images, right? So you don't have to have separate code to do that. You just put the image in whatever size it is, and the model has a layer that does that for you. So your model is pretty flexible.
Hey guys, I didn't catch the whole conversation, but I just wanted to say to your question, George, a minimum requirement for only doing the pre-processing once is all of your data needs to fit in memory. Mm-hmm. So if you don't meet that requirement, then it's impossible. It's going to have to reprocess it. So so there you would have to manually process it and save it off, because there is the caching option in whatever tf.data, and so you can cache and shuffle and that'll, I think it'll only do it once, but only if it all fits in memory.
Well, that depends on what type of.
Then the other parameter is.
Does that not depend on what type of processing you're talking about? If you're just calculating means and variances or something, you could do that just by adding sums and squares without storing. Not everything has to fit.
I don't understand. I mean, if you have 100 billion examples. Oh, you're talking about like fitting a normalizer?
Yeah.
Yeah, I don't know about that, but I'm just saying for other operations, you're doing it to the example. And
Right.
so even if you fit it and you only stored the normalization parameters, you're still normalizing each row on the fly, right? But the other comment I was going to make is if you're doing a lot of your training on a GPU, then if your CPU can keep up, then you don't actually pay any penalty for pre-processing over and over again if the GPU is your bottleneck. So so if the CPU can feed, 1,000 records per second and the GPU can only process 100 records per second, then it really doesn't matter that you slow down your CPU, so now it can only do 800 per second. It's still way faster than your GPU. I'm not saying that's always the case. I'm just saying if that's the case, then
I'm curious. I mean, just from a performance perspective or like optimization, but we'll get there, I guess. Yeah.
Yeah.
I guess that's what week 4 is going to be about.
Cool. Looking forward to it. All right, friends, I'm going to stop the recording here for our YouTube folks and everybody else who couldn't make it today. Thanks for joining us. I'll leave the floor open for discussion if you want, but again, looking forward to seeing you everyone next week. We'll continue with the notebook that Robert discussed. All right, friends.